So, what we'll be looking now is the aspect of ensuring or guaranteeing nobody essentially modifies your operating system or your applications when it is essentially stored in the disk, right? So, what do you mean by this? So, you have your processor, right? And what we've seen during the course is that once you give this processor the reset vector, and of course it is powered on and it gets its clock source, so it essentially starts booting up and then eventually boots up your operating system and starts executing your OS, right? So the first thing that executes is what we call as a bootloader. So what the bootloader code does is that it reads the OS image from the secondary storage, for example, the hard disk or the flash, loads it into memory, and starts executing it, right? So your processor, if I have to essentially draw a very high level diagram of it, is connected with the RAM, but also is connected to your secondary storage device. Right? For example, the hard disk. So your image of your operating system, which essentially boots up your system and starts executing processes and so on, is going to be part of the secondary storage, right? So this over here would be your your image of the OS. Okay, so when your processor is reset, you have a bootloader that is executing in the processor, which essentially starts up your processor, does some very initial little initializations, like for example initializes the RAM, maybe some other peripherals and so on, and then copies this image from your secondary storage into the RAM, right? So now you have the OS image copied into the RAM, right? And once this is done, your processor can then start to execute your operating system. So the problem that we face here is that an attacker may be able to, when the system is turned off or when the system is not powered, can be able to say modify the secondary storage and change the image of the OS. So for example, the the attacker could possibly tamper with this image of your operating system stored in the secondary storage, and therefore when the processor starts its execution, the bootloader that loads the kernel or the OS image from the secondary storage into RAM would also be tampered, right? Now this can be bad because now your operating system itself that executes is tampered. And as we have seen in the previous video, what it means is that if you do not trust your OS, or if you are running an OS which itself is tampered or modified, then it means that every process or any application that you execute could is essentially unsafe. So how do we essentially prevent this? The way to essentially handle this problem is what we call as the secure boot. Okay, so this is what we'll be looking at in this video. So what we intend to do is to secure the data that would include your OS image, or for that matter any data that is present in any application uh, which is essentially stored in your secondary storage. So this is done with the help of secure boot. So just to summarize what we have discussed so far, why do we need secure boot is because the attackers may essentially replace the software or tamper with the software or the operating system that is stored in, say, your flash memory or your hard disk, and this tampered data, when it essentially executes, would automatically be compromised, right? So how do we achieve the secure boot? Is by creating what we call as a secure chain of trust. Starting from a root device which we inherently trust, and sometimes this root device is called the root of trust, we essentially build up the security of the entire system, right? And the objective of this root of this secure boot is to essentially detect any such tamper that is present in your system, right? So the basic idea of the root of trust is to have a very small component called, sometimes called the TPM or trusted platform module. Sometimes it could be a physically unclonable function, or it could be an on-chip memory which is inherently secure. So this inherently secure component is the root of trust, which essentially guarantees that the image that you are essentially loading is essentially authentic. So when your processor essentially starts to execute or is reset, it starts with this root of trust. The root of trust first needs to load the bootloader into memory, right? So before it essentially loads it, it validates with the help of a digital signature whether the bootloader has been tampered or not, right? So this is done. This is essentially validated with the help of keys that are stored within the root of trust, right? So only if the signature is validated would the bootloader be permitted to execute, right? So now we have a validated bootloader which starts its execution on the processor, and after it does its initialization, it initializes some of the peripherals, memory, and so on. It needs to essentially start to execute the operating system. But as before it loads the OS into memory, it would need to check the validity of the OS image. Now, as before, again, this is done with the help of a signature, right? The signature for the OS is validated using keys which are stored uh, in the root of trust or the bootloader to ensure that the footprint of the secure OS is indeed correct and not tampered, right? So once this is done, your secure OS, which essentially runs in the trusted environment in the secure world, starts to execute. Now, just like before it essentially continues further and starts to execute various applications which are called trustlets. Signatures of each trustlet is validated to detect any tampering. In a very similar way, when the secure OS wants to load the rich OS, for example, the Android, the digital signature of the Android footprint stored in the flash is validated, and only if validated would it essentially start to execute, right? So what we have now achieved in this way is a complete chain of trust, starting from a root and then building ourselves up until we have the rich operating system that executes, right? So we are guaranteed this way with the help of strong cryptographic algorithms that any application within this particular chain is essentially authentic and not tampered in the secondary storage, right? Thank you very much.